Hello class, welcome to the Stat 215 Lecture 6 video. In this video we have three objectives. First, we are going to define the probability density function for a continuous random variable. Second, we are going to calculate probabilities for continuous random variables. And third, we are going to find the cumulative distribution function for our continuous random variable. To get started, let us recall the difference between discrete and continuous random variables. For discrete random variables, they are the set of possible outcomes that are countable. In our continuous random variable, we can take on values on a continuous scale. Usually this represents measured data, such as heights, weights, temperatures, distance, and life periods. This brings us to our first objective. Define the probability density function for a continuous random variable. This objective is pretty short and is only going to be our single slide. So for our probability distribution function, we cannot give it a table the same way we did with our discrete random variables. To define it, our probability density function, abbreviated PDF, is a function that specifies the probability distribution of a continuous random variable. To use our PDF, we have our objective 2, which is to calculate probabilities for a continuous random variable. So, for our probability density function, areas under our curve represent probabilities. So, for the probability of A less than X less than B is equal to the integral of f of x dx from A to B. We can see this visually in our function. This moves on to motivate us to define our probability density function. So the function f of x is a probability density function for the continuous random variable x defined over the set of all real numbers if f of x is greater than or equal to 0 for all x belonging to the set of all real numbers. 2, the integral of f of x dx from negative infinity to infinity equals 1. And third, that the probability of a less than x less than b equals the integral of f of x dx from a to b. Talking about the area under the curve, we need to note that the probability of a less than or equal to x less than or equal to b is going to be equivalent to the probability of a less than x less than b. This is only going to be true for continuous random variables. This brings us to our third objective, to find the cumulative distribution function for a continuous random variable. The continuous random variable f of x, often abbreviated as CDF, is represented by capital F of x, same way as we did with discrete variables. And we can say that of a random variable x with density function f of x, our CDF is going to be capital F of x equals the probability of x less than or equal to x is equal to the integral f of t dt from negative infinity to x for negative infinity less than x less than infinity. Therefore, the probability of a less than x less than b equals f of b minus f of a, and our f of x equals the derivative of capital F of x. Hopefully this hasn't been too bad so far. Okay, so for the remainder of this lecture, let's just take a look at about 3 examples, because I know I just threw a lot of information at you, and sometimes the best way to understand these concepts is through examples. Let's take a look at example 1. Okay, example 1. Suppose that the error in the reaction temperature in degrees Celsius for a controlled laboratory experiment is a continuous random variable x having PDF f of x equal x squared over 3, when -1 less than x is less than 2, and 0 otherwise. Using our PDF, we can make a graph. Notice when we are outside our bounds, our graph is at 0. Otherwise, we have a nice graph of x squared over 3 from -1 to 2. Now let's do some calculations. We want to first verify that f of x is a PDF. So one thing we can note is that f of x must be greater than or equal to 0 for all x, since our PDF has an x squared term. This brings us to our next part. We need to verify that the integral of f of x dx from -infinity to infinity equals 1. Let's check that out now. So, because the bounds of our function are from -1 to 2, we don't actually have to go from -infinity to infinity. And our function is x squared over 3 dx. Now that everything's set up, we need to simply integrate. So, using our rules of integration, we'll have 1/3 multiplied by x cubed over 3 from -1 to 2, which will equal 8/9 minus -1/9, which will equal 1. Perfect. Therefore, f of x is a PDF. Good job. Let's move on to our next part. Let us find the probability that the error in reaction temperature is between 0 degrees Celsius and 1 degree Celsius. Well, this is actually pretty easy. Let's start off by writing the probability of 0 less than x less than 1. For now, we will integrate our function x squared over 3 dx from our bounds of 0 to 1. Using our rules of integration once again, we'll have 1/3 multiplied by x squared over 3 from 0 to 1. This will equal, oops, forgot to write that as a 3. Typo. Hope I did that right above. Yes, I did. We're good. Okay. So, this should be 1 cubed over 9 minus 0 cubed over 9, which will equal 1/9. So, to answer the question, what is the probability that the error in reaction temperature is between 0 degrees Celsius and 1 degree Celsius is 1/9. Excellent. Let's move on. Now we would like to specify that the CDF for x and use it to find the probability of 0 less than or equal to x less than or equal to 1. Okay, no problem. So start off as capital F of x and large curly brackets. Same as with our discrete random variables, we know that at the end of our bound, it is 0, so x is less than or equal to -1. F of x equals 0. And when x is greater than 2, f of x is equal to 1. Whoops, my hand just opened up jump. There we go, back to where we are. At this point, we've done our integration multiple times. We know that if we were to integrate x squared over 3 from -1 to 2, that equals 1. If we were just to perform the integration, as we've done multiple times here, we know that that's equivalent to x cubed over 9. That's the function we're looking for here. X cubed over 9 when -1 is less than x is less than 2. Not bad. Once again, f of x is equal to 0 when x is less than or equal to -1. F of x equals x cubed over 9 when -1 is less than x is less than 2. And f of x equals 1 when x is greater than or equal to 2. Now that we've done the first part, we can use our CDF function to find the probability of 0 less than or equal to x less than or equal to 1. So to copy that from above to keep things neat and tidy, we can use our rule from our previous slide that says the probability of a less than x less than b equals f of b minus f of a. So this is going to be f of 1 minus f of 0. Plugging in 1 cubed over 9 minus 0 cubed over 9, which equals 1/9. There we go. Same as above. Two ways to solve the same problem. That can come in handy. Now that we've finished off our first example, whoops, not quite finished, let's do a quick graph of it. So, graphing our CDF, when we are less than -1, we're at 0. Greater than 2, it's at 1. In other words, otherwise, we have our graph of x cubed over 9. Pretty simple. Now, we can actually take a look at our example 2. Based on extensive testing, it is determined by the manufacturer of a washing machine the time x in years before a major repair is required is characterized by the probability density function f of x equals 1/4 e to the negative x over 4 when x is greater than 0, 0 otherwise. First, we want to know what is the probability that is at least 6 years before a major repair occurs. Well, let's try to figure that out. So really what we're asking is to find the probability of x greater than or equal to 6. Okay, let's do it. So if we recall from our previous slide, f of x equals 1/4 e to the negative x over 4 when x is greater than or equal to 0. So this means in order to find the probability of x greater than or equal to 6, we will need to integrate our function from 6 to infinity. In order to do that, we need to take the limit as t approaches infinity of our function from 6 to t. So now we need to find the integral of 1/4 e to the negative x over 4 dx from 6 to t. At this point, we're going to use some substitution. So we are going to let u equal x over 4 and du equal 1/4 dx. By substituting in, we will now integrate e to the negative u du from 6/4 to t over 4, which would equal negative e to the negative u on our bounds from 6/4 to t over 4. This would equal negative e to the negative t over 4 plus, remember, minus minus makes a plus, e to the negative 6 over 4. Now, if we take the limit as t goes to infinity of e to the negative 6 over 4 minus e to the negative t over 4, that will give us e to the negative 6 over 4, which will give us our probability of 0.2231. Wow, that was a lot of work. Bright news for us, there's actually another way to calculate this, and a way that I personally prefer. So, to start off, let's acknowledge that for x greater than or equal to 0, f of x equals 0 to x for 1/4 e to the negative t over 4 dt. This means that if we integrate, we have negative e to the t over 4 from 0 to x, which is equivalent to negative e to the negative x over 4 minus negative e to the 0. Remember, anything to the 0 is 1, so this is going to be equivalent to 1 minus e to the negative x over 4. Okay, so pulling back, we recall that f of x equals the probability of x less than or equal to x, which we have now calculated to be 1 minus e to the negative x over 4. This is important. Why? Because we are very lucky because we have the rule of the complement. So instead of doing the probability of x greater than 6, using our rule of the complement, we can do 1 minus the probability of x less than or equal to 6. Again, that is the complement rule. Now, it's just a matter of plugging in. 1 minus, so probability of x less than or equal to 6, we can use our function above. So that's going to be 1 minus e to the negative 6 over 4, which we can simplify to e to the negative 6 over 4, or once again, 0.2231. Personally, I prefer using the rule of the complement. So anytime you're dealing with a continuous random variable and you are asked to find the probability of x greater than x, automatically start thinking the complement rule. Doing 1 minus the probability of x less than or equal to x is going to be usually much easier. Little helpful tidbit for down the road. Let's continue on. So, still working with our second example, we are wondering what is the probability that a major repair is needed in the first year? Okay. This should not be too bad. In order to know if a repair is needed in the first year, we want to find the probability of x less than or equal to 1. Okay, so at this point I'm going to draw a little star because I want to recall what we did in slide 20. And that is when we determined that f of x equals the probability of x less than or equal to x, which equals 1 minus e to the negative x over 4. That second option is really come in handy because now we just need to do some plugging in. probability of x less than or equal to 1 is 1 minus e to the negative 1 over 4, which will equal 1.2212. Not bad. We could have also done this the long way, which would have been to perform the integration. So if we want to do the probability of x less than or equal to 1, we would integrate our function 1/4 e to the negative x over 4 dx from 0 to 1. Integrate, we would have negative e to the negative x over 4 with our bounds 0 to 1. Plug in, this would be negative e to the negative 1/4 minus negative e to the 0, which would equal 1 minus e to the negative 1/4, which equals 0.2212. So either way, we're going to come up with the same result. There's just ways we can go about it faster, but ultimately, it's going to be up to you. Let's take a look at our last part of example 2. We want to find the probability that a major repair is needed between year 1 and year 6. Once again, there is 2 ways to go about it. Option 1 is to perform our integration on our function 1/4 e to the negative x over 4 dx from 1 to 6. The second option is to use our rule that says, here, let me just complete the first part. Remember, we're trying to find the probability of 1 less than or equal to x less than or equal to 6. So the alternative for this is to use our rule that the probability of a less than or equal to x less than or equal to b equals f of b minus f of a, but we also know that f of a number is really just the probability of x less than or equal to that number, meaning this would really be f of 6 minus f of 1, which is equivalent to the probability of x less than or equal to 6 minus the probability of x less than or equal to 1. I know that might be a bit confusing, so you should definitely go back and review. At this point, we can use our rules. We know that the probability of x less than or equal to 6 is 1 minus 0.2231. And we know that the probability of x less than or equal to 1 is 0.2212. Now, simple math, you'll get a result of 0.5557. So, what is the probability that a major repair is needed between year 1 and year 6? The answer is 0.5557, or about 56%. Not bad. Now, at this point, let's move on to our third example. Example 3. We are going to let f of x equal 1/2 e to the x for 0 less than x less than a, 0 otherwise. We want to find the value of a that makes f of x a PDF. Notice the graph of our function. Okay, so let's think about this for a second. Well, we know in order for something to be a PDF, that means when we integrate, it must equal 1. Correct? That's correct. So, with our function, f of x equal 1/2 e to the x for 0 less than x less than a. Let me double check that that's right. Yes. Okay. So that means 1 must equal the integral of 1/2 e to the x dx from 0 to a. Now it's just a matter of solving. So if we integrate, we have 1/2 e to the x from 0 to a. That will equal e to the a minus 1 over 2. At this point, we will set e to the a minus 1 over 2 equal to 1. And then we will simply solve for a. So this will give us e to the a minus 1 equals 2. E to the a equals 3. Now we will take the natural log. So we'll have a equal to the natural log of 3, meaning our a will equal 1.099 approximately. So to answer our question, we want to find the value of a that makes f of x a PDF. That value is a equal to 1.099. Okay, that brings us to the end of our section. Let's just do a quick review. So, things we learned. We learned how to use a probability density function to calculate probabilities for continuous random variables. We also learned, and hopefully it was a review, that the total area of the curve equals 1. Okay, so that brings us to the end of the lecture. As always, if you have questions, send me an email, and don't forget to read your homework and do your reading. Have a good night, everyone.